Hello everyone, my name is Chirag Agarwal and I welcome you all to my talk on a rigorous theoretical analysis and evaluation of graph neural network explanations. As graph neural networks are increasingly employed in real-world application, it becomes critical to explain the model predictions to the corresponding stakeholders. While several GNN explanation methods have been proposed recently, there has been no work on their theoretical analysis. In this work, we introduce the first axiomatic framework for theoretically analyzing, evaluating, and comparing state-of-the-art GNN explanation methods and formalize the three important properties of faithfulness, stability, and fairness necessary for developing safe and reliable GNN explanations. We now move to the first pillar of faithfulness. A reliable explanation should faithfully capture the behavior of the underlying model. An explanation corresponding to a node U is faithful if it accurately captures the behavior of the underlying model in the local region around node U. In order to quantify faithfulness, we generate k perturbations of node U. This is done by adding some random noise to the node attributes for node U and modifying the edges associated with node U. Formally, we say that given a set K comprising of a node U and its perturbations, an explanation EU corresponding to node U is faithful if the difference between the predictions using the original node attributes associated with node U and the predictions generated using the masked node attributes using the explanation EU is less than some delta, which is an infinitely small constant. We now move to the second pillar of stability. A key trait for a reliable explanation is that it should exhibit stability. That is, infinitely small perturbation to an instance which do not affect the model prediction should not change the corresponding explanation drastically. In the context of graph neural networks, an explanation corresponding to node U is considered stable if the explanations for node U and its perturbed node U prime are similar. Unlike faithfulness, we just generate one single perturbation of node U by adding random noise and adding or deleting some edges, and define stability as given a node U and its perturbed node U prime, an explanation EU corresponding to node U is said to be stable if the distance between the explanation for U and U prime is less than or equal to some delta. We now move to the third pillar of fairness. For fairness, we define both counterfactual and group fairness for an explanation of node U. An explanation EU corresponding to node U preserves counterfactual fairness if the explanations for U and its sensitive attribute perturbed node US are similar if the model predictions are similar and vice versa. In order to generate a counterfactual node, we flip or modify the sensitive attribute of node U. Now we define counterfactual fairness. Given a node U and its sensitive attribute perturbation US, an explanation EU for node U is said to preserve counterfactual fairness if the distance between the explanations for node U and node US is proportional to the difference between the predictions from the subgraph associated with node U and node US. With respect to group fairness, an explanation preserves group fairness if it accurately captures the statistical parity of the underlying model F in the local region around node U. Similar to the faithfulness property, we generate k perturbations in the local region around node U and define group fairness as given a set K comprising of node U and its perturbations, an explanation EU for node U preserves group fairness if the difference between the statistical parity calculated using the predictions of the original node U and its perturbations and the statistical parity calculated using the explanation mask of node U is less than or equal to some infinitely small delta. We now define the 4 evaluation metrics used in our work. The unfaithfulness metric measures the difference between the predictions made using the original and the marks node attributes. The instability metric measures the L1 distance between the explanations generated for the original and the perturbed node U prime. The counterfactual fairness mismatch metric measures the normalized L1 distance between the explanations generated for node U and the counterfactual node US. The group fairness mismatch metric measures the statistical parity for a group K of predictions using the original attributes and the marks node attributes. We now move to a verification of our theoretical bounds. In the figure, we see the empirically calculated unfaithfulness in red and our theoretical upper bounds for faithfulness in blue across 9 different GNN explanation methods. The empirical values and the theoretical bounds for unfaithfulness indicate that no violation of bounds were detected in our experiments. These results show that the empirically calculated unfaithfulness are lower for explanation methods with smaller theoretical bounds, suggesting a strong correspondence between the empirical calculations on real-world dataset with our theoretical bounds. We found similar trends for the bounds calculated for group fairness metrics too. To conclude, our work presents the first axiomatic framework to theoretically analyze, evaluate, and compare state-of-the-art GNN explanation methods. Our experiments with multiple real-world datasets evaluate the reliability of several state-of-the-art GNN explanation methods using model properties like faithfulness, stability, and fairness. We further show that how some GNN explanation methods perform on par or worse than random explanation techniques. Our paper for this work is up on arXiv. Kindly check it out for a detailed set of proofs regarding the different model properties and more experimental results comprising state-of-the-art GNN explanation methods. Thank you.